Hello everyone, and welcome back to Night School. This is Night School 7, Stability Design of Steel Structures, Applying Modern Methods of Structural Analysis, presented by Donald W. White and Ronald D. Zemian. Today is March 2nd, 2015, and this is Session 5, the AISC Direct Analysis Method from Soup to Nuts. Today's presentation will be presented by Dr. Donald White. My name is Brent Liu. I'm with AISC, and I'll be moderating today's presentation. I want to introduce today's speaker. I want to welcome back Dr. Donald W. White. He's a professor at the Georgia Institute of Technology. Dr. White's research covers a broad area of design and behavior of steel and composite steel concrete structures, as well as computational mechanics, methods of nonlinear analysis, and applications to design. Dr. White is a member of AISC's Committee on Specifications and has also served as the past chair of SSRC, the Structural Stability Research Council's Task Committee 29, which is Inelastic Analysis for Structural Design, and Task Committee number 5 on beams. Dr. White has received many awards throughout his career, including the Special Achievement Award from AISC in 2005. He received the Shortridge Hardesty Award from ASCE in 2006. Once again from AISC, in 2009 he received the T.R. Higgins Lectureship Award, and in 2010 he received the Raymond C. Reese Prize from ASCE for his research and development activities in the area of stability analysis and design. Please welcome back Dr. Donald White. Don, thanks for being here. I'll hand things over to you.
Okay, thanks Brent, and welcome to everyone. See if we can get this going here. All right. So this is Session 5 in our 8-part series. So we're over the hump. It's all downhill from here. In this session, we'll first focus on an overview of the key concepts associated with the AISC Direct Analysis Method. And then next, we'll review specific details of the AISC Stability Design Methods with particular emphasis on the DM. Then in topic 5.3, we'll look at important considerations related to modeling of nominal out-of-plumbness effects in ordinary building structures. We'll then focus on a specific single-story multi-bay frame example to get a better understanding of how the direct analysis method works in topic 5.4. Next week we'll look at a multi-story building frame, and then the following week we'll look at some other structures and applying direct analysis method and other methods. And then tonight we'll wrap up with topic 5.5 in comparison to test simulations with a single-story frame that we're going to study. Similar to last week, much of the background to the presentations comes from AISC Design Guides 25 and 28. So these are good companion reading materials. And let's get down to business with the first topic. So Chapter C of the AISC specification lists 3 sanction methods of stability design: the direct analysis method, the effective length method, and the first order analysis method. The first order analysis method is really the direct analysis method with embedded second order elastic approximations that are conservative up to the limits of the use of the method. And so that's all I'm going to say about the first order method tonight. We'll focus on the direct analysis method and the effective length method in the remainder of the discussions. The AISC specification gives the direct analysis method as the preferred approach, and we'll try to understand why that's the case as we go along. First, a couple of notes about what design means. Basically, of course, it generally means selection of constructional configuration. Also, we're looking at performing an analysis of that configuration and proportioning components. And so basically, with the exception of Appendix 1, which I think Ron will talk a bit about in the 8th week, all the design methods that we're going to be looking at here have requirements for structural analysis in them, and also rules for checking of the component resistances that are tied to how we do the analysis. So basically, analysis rules and checking of component resistances always go hand in hand, and the rules for checking vary as a function of the analysis requirements and vice versa. So since emphasis is on direct analysis method here, what's it all about? Basically, we're looking at assessment of overall system structural stability, including effects of geometric imperfections and reduction in stiffness as we're approaching the ultimate strength limit state. And we want to do that explicitly in a second-order load deflection structural analysis. Why is the direct analysis method preferred? It's generally more straightforward once you get used to it. By moving some of these considerations over to the structural analysis, we're able to simplify what we do on the resistance side. And so some of the complications associated with effective length factors and their proper calculation go away. Basically, we take K equals 1 in all cases and treat the members as if they're braced in the resistance calculations. The direct analysis method tends to give us a better, more representative accounting of what the actual real forces are internally within the structure. And the direct analysis method is more general in the sense that we could apply it to sway frames, braced frames, combined frames. All the applications work the same way for all types of structures. To get started understanding the different stability design methods in AISC, we could go to section C1 that lists various general requirements. And this section basically says that any method of design that is addressing stability must consider each of the things that you see listed here on this slide. Now, considers is an important operative word. Basically means that as the engineer of record, if you've considered a particular attribute or effect and you've deemed that that's not important, you've done your job. It's gone. It doesn't mean that we have to take the kitchen sink and throw it at everything out there. Let's take a few slides and scrutinize each of these requirements. So first of all, the component limit states. Basically, we need to deal with the member axial resistance, the flexural resistance, the combination of those in the beam column unity checks with all the members. And also when we're looking at connections, panel zones, stability bracing, basically we have to look at the direct limit states that are associated with modes of failure, potential modes of failure for all the components in the structure. Now the beam column unity check interaction equation that you see here, this bilinear equation is of course this is kind of the staple of what we use in the AISC provisions that ties things together in terms of strength ratios for axial, strength ratios for moment, and then essentially combined net strength ratios when we're checking members subjected to combined axial load and compression. There's some definitions on the subsequent slides here, similar to last week. I've embedded a number of definition slides throughout to just basically help you with grasping any of the terms that may be unfamiliar. So let's move on to slide 22. Look at the second basic requirement, and that's flexural, axial, and shear deformations need to be considered where important by modeling the corresponding component flexibilities in the analysis. Again, if shear deformation is not important for the structure you're looking at, for the component you're looking at, then you need not consider it. But if it's having a significant effect, you should. We talked about second order effects last week. Here we're looking at the fundamental definition of P large delta effect. It's basically the additional moment or couple due to the axial force acting through the relative transverse displacement of the member, if this is a member we're looking at here, or if this is a segment or an element, what is some length along the member, then it's the segment. You can have a P delta effect at the element level, the segment level, the member level. We also talked about P small delta effects last week. So P small delta formally we could say is the additional moment due to the axial force acting through the transverse displacement of the member due to its curvature, displacement relative to the member or segment chord. Now, any second-order analysis method is permitted by the specification as long as it's sufficient. And we talked a lot about what does sufficiency mean, or what do we need to do to make sure we're getting sufficient results last week. Skipping one slide ahead to slide 26, basically when we design by allowable strength design, we need to consider that we need to actually scale up our working load levels from allowable strength design to an ultimate strength design level by this factor alpha that we talked about last week of 1.6. We then generally conduct the analysis. We then divide back through the internal forces we get by 1.6 to get essentially to a pseudo allowable strength design internal force levels for our design by allowable strength. And so that's a bit of some algebraic gymnastics here. If we're actually using the amplified first-order methods, things are a little less confusing, you could say. Basically, in this case, the alpha 1.6 is generally buried in the amplifier in the load term there within the denominator of the amplifier. And so these complications don't quite show up, but we're really doing the same thing. We're getting an amplification at the ultimate strength load level and then applying that to the first order forces that are calculating at working load level. Another important point to always keep in mind when you're doing your second order analysis, it's essential to include all gravity or other load effects that influence the structure's stability. So any loads in gravity columns, in walls, etc., that are stabilized by the lateral load resisting system but otherwise aren't being included in the analysis, you need to include them or include their effect in some way. This is often handled by the use of a dummy column. That's not a stupid column, but it's basically a column that we would attach to the lateral load resisting system of the structure. We pin it out at all the levels, and then we connect it by pin struts back to each level of the building structure. And then the total vertical loads that are transferred to all the columns, walls, etc., that aren't actually being included directly in the structural analysis model get placed on that dummy column. You always want to make sure you give this dummy column enough area so that you're not squashing it. But that's a fairly common modeling approach that we can use here to pick up all the effects of gravity columns in the structure. We're not going to look at a specific example of this tonight, but we will do some specific things with dummy columns in the examples, some of the examples we're working next week. Okay, about the fourth and fifth requirements from the AISC specification for any stability design method. Basically, any of the methods have to consider geometric imperfection and stiffness reduction effects, and all of them do. Basically, we are dealing with handling initial geometric imperfection effects within fabrication and erection tolerances as specified by the Code of Standard Practice. And reductions in stiffness, those are also included in all the methods. Now, in the traditional effective length method, we're handling these effects on the overall system stability via only the member axial load capacities, P sub C back in the strength interaction equation, written in generic terms for ASD or LRFD. And we're doing that commonly by calculating effective length factors greater than 1, but alternatively, the corresponding we can do a corresponding system buckling analysis in order to get the underlying side sway buckling loads that then we can map to column strength. And the column strength equations with the K factors, basically where we're accounting for the imperfection and stiffness reduction effects in the ELM. Now, this works, and it's worked fine traditionally for moment frames, but only for moment frames and only for the beam columns in these frames. In actuality, if you look at what's happening, since we're only acting on the piece of C term in the beam column interaction check or in the column equations, then there's nothing explicitly coming into showing or handling how the imperfections or stiffness reductions impact your connections, the beams in the structure, etc. And so for design by the effective length method, the 2010 specification also requires consideration of sway imperfections. That would be an out of alignment or out of plumbness, delta naught over L of 0.002 or 1 in 500. And we need to do that with gravity, all gravity only load combinations within the structural analysis. The DM accounts for these effects explicitly in the structural analysis across the board. We're looking at a stiffness reduction effect that tries to handle the stiffness reductions that are handling as we're approaching ultimate strength. Also, we're handling nominal geometric imperfection effects directly in the analysis model for the DM. And then lastly, the sixth requirement is uncertainty in stiffness and strength. The ELM accounts for these uncertainties only via the phi and omega factors on the component resistances. If we go to the DM, part of the stiffness reduction that we're going to look at taking in the DM accounts for uncertainty in the structure's stiffness at strength load levels. Now, if you have a structure that's very stiff and subject to the light loads, well, if you take a stiffness reduction on something that's essentially rigid, you've still got something that's essentially rigid. So in that case, there would be a very small effect. The structure would be insensitive to the stiffness reduction and the overall second order effects for that matter. However, if you have a structure that is relatively flexible, subjected to large vertical loads, then this stiffness reduction can have a significant effect on the deflections and on the internal forces in the structure. And this characteristic is, of course, captured inherently by the direct analysis method. Why is the DM preferred? Well, basically, finding the effective length factor for general building systems where we have some combination of moment frames and braced frames can be complicated. And if it's a nice rectangular box, it still can be complicated, but put in a few setbacks and irregularities, which are, of course, very common, then it becomes very difficult to really get it right in terms of calculating the effective lengths. Also, the physical behavior of even the most basic frames is really never a bifurcation problem, whereas the effective length method tends to focus on let's use the bifurcation, a theoretical bifurcation response as a base. Nothing wrong with doing that, but the direct analysis is arguably a better way. It basically considers the fact that any structure is going to have incidental imperfections, and so that means that you put load on it, you always get a general load deflection problem involving the loading and bending of the structure. So say, for example, if we went in the lab and constructed just a nice cantilever column on some base, and we went to load the column by a nominally concentric axial load, well, we can't build that column perfectly plumb or perfectly straight. The Code of Standard Practice out of straightness limit is L over 1,000 in terms of the maximum. The maximum out of plumbness tolerance is L in 500. So if we have imperfections in those orders of magnitude, you load with the concentric axial load, you're going to get some bending at the base. And of course, we would want to design that base for some moment in general. And so the direct analysis method is looking to calculate the influence of the geometric imperfections on that base moment. Say if we've got some moment rotation characteristics that are nonlinear that might be associated with partially restrained base conditions, things get a little bit tricky to sort out exactly how to assess things in the effective length method, where we only consider the axial load, and in the plot on the right, we just load up the vertical axis but we need to calculate a K factor and calculate a PN based on KL, where we basically say, well, if we reach that for P, we're done. With the direct analysis method, we're basically considering even this case as a beam column. Our column and our connection are subjected to axial force and moment, and by doing so, even though it's a cantilever column, we consider it essentially as braced. Some of the things we'll talk about subsequently, we could even consider just the cross-section resistance of the column, as I'm showing you here, with anchor points on the vertical axis of PY and anchor point on the horizontal axis of MP. So in summary here, the basic concept of the direct analysis method, we want to estimate the required forces using a second-order load deflection analysis, and we want to account for nominal stiffness reductions at the strength levels, geometric imperfection effects in that analysis. Once we've got our force strength requirements from that analysis, then we are looking to check the member resistances, and that's where we account for strength limit states. Most of the strength limit states are not captured in the analysis itself. The limit states, the overall stability effects are captured in the analysis, but then the different component limit states we need to capture by resistance equations. All right, so that brings us to topic 5.2, where I'd like for us to look at a little more detail at specifics of the methods. And then once we've looked at this topic, and into 5.2 would be a good place we might stop for questions if there are any. So again, not to belabor the point, but what's the primary distinction of the direct analysis method? We're looking to handle the assessment of overall system structural stability, including the effects of geometric imperfections and reduction in stiffness as we approach the ultimate strength, explicitly within a second-order load deflection structural analysis. And by doing that, that's a little more work for the analysis, but we get a benefit in the strength resistance checks that we do. We basically don't need to look at use of K factor or K greater than 1 to evaluate the side sway resistance of moment frames. We basically look at design of the members considered as if they were braced in all our resistance calculations. We're not covering all the bases within the second order global structural analysis. The analysis generally does not have information built into it that captures things such as the yield strength of a material, such as what the different potential failure modes are. So we need to go to our resistance equations given the required strengths in order to complete all the bases. Now you won't find the terms that you see at the top of this slide in the AISC commentary or specification or in Design Guide 28, but this is I like to use these terms to help understand is what we're doing with some different caveats that we have in the specifications when it comes to applying direct analysis method or effective length method. If we have something that we would classify as a stability critical structure, it basically typically means we've got high axial load, potentially low lateral stiffness, and if you have a small change in the lateral load or the lateral stiffness or a lateral imperfection on the structure, it could result in a relatively large change in the vertical load carrying capacity. That's basically given by or represented in my little plot here by the curve that looks like it's showing up with higher member axial force. We changed H and the vertical load capacity changed noticeably. However, a stability non-critical structure, typically stiff structure, relatively stiff compared to the vertical load that it's carrying, and in that case you change H a little bit and you barely know it. So that's represented kind of by the green curves down that are we call force point trace curves in member internal axial force versus internal moment in my plot here. And you can say, oh, we changed H a little bit, but we probably got the same curve. And so basically, for a non-critical structure, AISC is simplifying the rules, or allowing you to simplify the rules for applying the methods, so that you're basically not saying, hey, gosh, why did I do all this and nothing happened? The definition of stability critical is basically when the second order amplification, so the second order drift over the first order drift, is greater than 1.7. If we're looking at the direct analysis method with the reduced stiffness we're going to be talking about, or greater than 1.5 with the unreduced stiffness or nominal stiffness we use in the effective length method. Now this slide is basically my attempt to capture everything in terms of all the specific rules about the direct analysis method and the effective length method in analysis requirements. So the direct analysis rules on the left in blue, the effective length method rules on the right in peach. So direct analysis method, we are required to model an out-of-plumbness of LN500 for gravity-only load combinations if it's a stability non-critical structure. We can do that with equivalent notional lateral loads if we want. In addition, we're required to use a 0.8 stiffness reduction on all contributions to elastic stiffnesses. And if we have members with high axial load, we use a column inelastic stiffness reduction factor of tau B on the rigidity of those members. You can see I'm using the same style that I gave you last week, where I'm showing equation C2-2b. So that is to reference you back to the specification where any equations that I'm using from the specification show up. Now, if we've got other materials that other than steel, we use 0.8E unless the code requirements for those materials have a smaller elastic stiffness. Now, in some cases, using tau B or putting that into our analysis, particularly if the software doesn't assist us in doing that, can be kind of a royal pain in the neck. And so the specification gives us an out where basically if we model a larger out-of-plumb imperfection than 0.002L, we kick it up by 50% to 0.003L for gravity-only load combinations, then we don't have to consider tau B. We basically use tau B equals 1 throughout. In addition, same issue with the 0.8E that we had in the blue, kind of the base darker blue rules above. Effective length method, we basically, for gravity-only load combinations, need to model the out-of-plumbness. Other than that, we use the nominal elastic stiffnesses. So these are the analysis requirements for the two methods. Well, what do we get in the direct analysis method by going to additional modeling detail? Basically, direct analysis method allows us to use K equals 1 in calculating the column capacities. Now, an appropriate braced column K value could be used, but we don't usually bother since the additional benefits of doing that are often small. Now, in addition, Design Guide 25 provides an extension to the specification, and some of these rules are being considered for adding to the specification in 2016. If the design axial load, alpha PR, at strength over PEL, where PEL is pi squared EI over L squared of the member in the direction of buckling, that's less than 0.1. Design Guide 25 basically points out that, well, you can use actually the strength based on K equals 0, or actually the cross-section strength when you're looking at flexural buckling limit states. Also, if you're modeling out of straightness in the members, you're allowed to use the cross-section strength in your calculations of PC. We'll look at particularly at some examples next week where actually the week after next, where that's very beneficial. We'll talk about that a little bit tonight as well. Effective length method, we always calculate PC based on a system buckling analysis. So for a sway frame, for most columns, that would mean we're using a K greater than 1. Except there's an exception here that if V2 is less than 1.1, we're allowed to calculate the column resistance based on K equals 1. A note about stiffness reduction, the elastic modulus E shows up in a lot of our specification resistance equations. Often that's only for normalization purposes. Where it does show up for other reasons than that, any stiffness reduction effects are already implicitly taken account in the specification resistance equations, so you'd never reduce E when you're plugging into the resistance equations of the specification. In addition, the stiffness reduction is basically intended to account for the effects of loss of stiffness as we're approaching ultimate strength levels. That means then there's no need to do that stiffness reduction at service load. Also, when we look at the load codes, basically looking at response spectrum analyses and requirements for that, or building period calculation, those requirements are based on nominal E, so we generally don't take any stiffness reduction there either. All right, well, what if we've got a stability critical structure? Well, in this case, the specification disallows the use of the effective length method. And for the direct analysis method, everything is the same as what I showed you in the previous slides, except what I have underlined here. Now we are required to incorporate the out-of-plumbness effect or the out-of-plumbness directly in all load combinations. That's pretty much the only difference there. We've now got a structure where that out-of-plumbness effect could be having a significant influence on the overall load carrying capacity of the structure, and so we need to consider it. As far as the resistance rules are concerned, this is exactly the same as what we had before. So the same requirements that we talked about earlier. Last thing in terms of kind of wrapping up with looking at a number of specifics of the effective length method rules and the direct analysis method rules. Why do we use the column strength calculation P sub C based on the actual unbraced length L, or K equals 1, in the direct analysis method? It's important kind of to understand this to kind of have your head around the whole process that we're working here. And the basic reason for that is to capture all the bases for situations where potentially you could have a structure you're checking where for some reason you have a very light column or beam column, say, that's subjected to large axial loads. And so in that case, the rest of the structure, either braced frame or moment frame, could be stiff enough where it's essentially preventing the sway of this light member. But this light member, if it's light enough and heavily loaded enough, could essentially get crunched in a non-sway buckling mode. And to cover the bases with that and to kind of keep things simple for routine analysis, we use K equals 1 or P sub C based on the actual length. Now, there's an alternative procedure from Design Guide 25 that's an extension that I talked about a little bit in the tables I gave you. And some of these extensions are being considered for addition to the specification in 2016. And so that's basically the flexural buckling axial resistance, either PNX or PNY, can be taken as PN based on L equals 0, or in the current spec that would be our form factor Q times the yield load PY. If, again, the alpha PR is less than 10% of the loader load in the direction of buckling, or if an appropriate out of straightness is included in the analysis. That can be a bit of trouble for routine structures, so we don't usually want to bother with it there, but there's other cases where it can be very useful to be able to do that. Now, when it comes to torsional or torsional-flexural and or lateral torsional buckling limit states, we still need to do the strength checks with PN and MN using the actual unbraced lengths. That's the reason for that is that the direct analysis method really doesn't have the resolution to be able to capture these limit states in general. And as we were just talking about last week, most design software does not include the consideration of warping rigidity, and so we're somewhat limited in being able to really do an accurate characterization of torsional, torsional-flexural, lateral torsional buckling limit states. Brent, I guess this would be a good time. If there's any questions that have come in, we could stop and chat about those.
Okay, Don. Yeah, we do have a handful of questions. We'll try to address a few of these before we move on. The first question, I want to go to slide 26, please.
Okay.
Is that the right slide? Yeah, okay. So
okay.
The question is using the alpha, the 1.6 for alpha. If the structure is a self-weight, gravity loaded only, or otherwise lightly loaded, such as during construction, must one use the 1.6 for ASD analysis and then divide back for a design check?
No.
The questioner is saying he finds that this typically doesn't matter and it's difficult to implement.
Right, it is kind of a pain in the neck, isn't it? Well, one, if you're using an amplified first order analysis, then it's not quite the same gymnastics that we would have to do with a general purpose analysis. And if you do have that sort of a structure, again, you could come back to what we were talking about earlier and kind of laying out things generally. If you're looking at a structure and say, hey, I've considered second order effects, and second order effects are negligible in this problem, as long as you're right, you're good. Okay, so you could approach it from that sense. In the general sense, basically, if there is a measurable second order effect, we need to capture that effect at the ultimate strength load level. So that's why we have to do these gymnastics.
Okay. Let's move on to slide 31, please.
Okay.
Okay, I think this is in regards to point number 1 there. So the question is this. Now, for the direct analysis method, are phi and omega not applied to member axial and flexural resistances?
Oh, of course. In the direct analysis method, you're basically picking up uncertainties in stiffness and strength in the application of phi or omega to the strength component strength terms, but you've handled the overall side sway effects in the overall analysis. And so when you're looking at what your resistance checks, you're kind of focused on, okay, you're treating it, the side sway effects have already been handled, and so you're kind of looking at each component as if it's a member, as if it's braced, you could say.
Okay. And then let's look at slide 38, please.
Okay.
Okay, so the question is, can notional loads be ignored if you're always applying wind or seismic load combinations?
Okay. Good question, and that's where the specification writers were very careful to basically not have something where you're putting in notional loads and then say, gosh, that notional load didn't do anything to the structure. And so a stability non-critical structure, you're required to consider your notional loads only for gravity-only load combinations.
Okay. And then one last question before we move on, slide 40.
Slide 40, okay.
The question is in regards to reducing the stiffness. Do we have to use the reduced stiffness E when calculating drift for second order analysis?
Yes. Ron used a term, and I'll probably mention the term again a little bit later tonight, that direct analysis method is kind of a poor man's test simulation analysis or test simulation check. And so that stiffness reduction is to account for the fact that as you're approaching ultimate strength limit, you are losing stiffness in the structure. And it's a kind of a very coarse accounting for that effect, but it is required.
Okay. All right. Let's move on. We were left off on slide 44.
All right. So topic 5.3 basically looks to dive down in a little more detail this one aspect, and that's the modeling of the nominal out-of-plumbness in typical building structures. And so that out-of-plumbness the base is delta naught of L in 500. That comes from the maximum tolerance in the IASC Code of Standard Practice. My preference is to explicitly model that out-of-plumbness in the frame geometry, but if it's not facilitated by the analysis software, it's kind of a pain in the neck to do that. The reason I prefer this is that if there's any questions that come up about what's my notional lateral loads, I always have to go back to the out-of-plumb structure to kind of figure it out. And so things are conceptually cleaner, easier to understand, and you could say easier to automate in terms of programming by just canting the frame. Now with that said, I know that most software providers prefer to use the notional lateral load. Reasons for that, notional lateral loads have been around in other international design codes much longer than they have been in the AISC specification. And so many of the providers already had notional lateral load generators that they were writing to service other codes. The other thing that happens is if you're doing a notional lateral load, your notional lateral load basically is being handled on the right-hand side of your equations for your matrix stiffness, net direct stiffness analysis. So it's a little bit more computationally efficient that way. If we were going to be looking at different out-of-plumbness, basically we have to build the left-hand side of the equations, the stiffness equations and all for different out-of-plumbness in order to handle that. But I would argue that that's really not a big deal unless you're trying to implement that in legacy software. That would be a big deal, right? Now the notional load equation is equation C2-1 that you see here. The notional load is 0.002 or 1 in 500 times y sub I, where y sub I is the vertical load applied at a given level. Just to want to point out in the specification equation shows alpha y sub I. Here in my presentation and also in Design Guide 28, we just use y sub I as representing, that's the load at ultimate strength that we need to bring in there in the equations. And so just kind of a little bit different terminology there, so don't let that throw you. Now, where does this notional load of 1 in 500 y sub I come from? This slide is intended to try to help get at that. Basically, it's a given story level with looking at the stories above and below that level. And so the top story here, if we have an initial out-of-plumbness of delta naught I plus 1, then the P delta shears, coming back to what we were talking about last week, that are associated with that out-of-plumbness are shown here on this highlighted view. Now if we go to the story below, same deal, but now the loads are P sub I, and let's suppose that we've got the same delta naught over L showing up at this story, which is going to be our base way of doing things with the out-of-plumbness. Now let's do Newton's third law. We basically look at equal and opposite reactions coming from above and from below at the story level. And if we sum those, the notional load is basically that sum. you can see that everything cancels out to where what we're left with is just the load that comes in at this level. So we use that and put that on the structure as a notional equivalent lateral load at each level of the structure. Now, where do we put these loads on? If we got a structure with flexible diaphragms or any other cases where the position of the vertical load in plan may have an important stability effect, then Y sub I's, you would consider it as the vertical load transferred to each column, etc., at a given level. And your notional load is a notional load that would be applied at each of these locations in the corresponding plan. So you can always come back and say, okay, let me look at every place where vertical load's coming on the column. I can put a notional load there. It's more convenient if we've got a structure where we're allowed to model the diaphragms as rigid to just get a total vertical load and then calculate it's the total vertical load that's coming on to the structure at a given level, and then the corresponding notional load that we could just apply at the center of the or centroid of the overall vertical loading on the frame. In terms of what direction do we apply the delta naught over L or the notional load? The spec says apply it for greatest destabilizing effect, which isn't all that difficult, but it does require some thought. And so we'll look at this a bit further in the following slides. In terms of the pattern, if we're looking at structures up to about 7 to 10 stories, supporting gravity loads primarily through nominally vertical columns, walls, or frames, the critical pattern is just a uniform lean of the structure, delta naught over L, all the way up the building, or we calculate the corresponding notional lateral loads that go along with that. Now, if we have a taller structure, Design Guide 28 has an appendix that provides some discussion about how you might consider an out-of-plumbness just on a certain group of stories at a time. What about applying the out-of-plumbness or notional lateral load for gravity-only load combinations? That's the one that shows up the most because most structures are going to be stability non-critical. Well, we need to apply them independently in the two orthogonal directions. And so similar to just how we work with the load codes, we approximate principal stiffness orientation of the structure. And so we say, okay, we need to apply either the out-of-plumbness or the notional load along each of the principal stiffness directions. Now, independently means here that we're required to do it only one orientation at a time. Generally, there's no need to consider off-axis notional loads. Just applying it to the principal directions is good enough. Generally, it's considered that torsional notional load or corresponding initial twist of the structure is not required. I'm aware of one case where the design engineers did take a look at torsional notional load effects or initial twist effects of a structure. That was with Halverson's office, where they were looking at a structure called a Moscow Tower, where the overall structural system was a cruciform. Of course, we know that a cruciform plan, that's going to be very torsionally flexible, and so they had some concerns there about potential torsional stability of the building. So in that case, they did look at a torsional notional load. But in general, we wouldn't bother to go to that trouble. Other information about gravity-only load combinations, where do we apply? What directions do we apply? Basically, we need to apply in the plus or minus directions along the two principal directions. So that means, in general, the simplest thing to do is just apply a total of what used to be one gravity load combination. Now for each gravity load combination, you've got 4. A little bit of a disadvantage there, but that's the only way we're going to account for these effects. And we're talking about doing this either in a direct analysis method or effective length method to try to get some effect of imperfections into beams, connections, etc. Now, if you have a relatively simple case where the structure does not have any side sway under gravity load, and if you enforce symmetry in the design by grouping of the design selections, then you could limit things down to just doing two cases, one in each of the, say, positive principal directions. Also, if you have a case where the structure's side sway deformations are in the same direction in all of its levels, then again you could apply in the plus or minus direction that would tend to increase the net side sway in each level. And so you could then get down to only two out-of-plumb values or two notional loads cases that you would need to consider. Direction that increases the net side sway, that's basically the meaning of increasing the overall destabilizing effects on the structure. And overall destabilizing effects, that basically what that means is if you look at some cases or some places in the structure, you could have a particular location where if you put the notional load on in one direction, it's going to reduce, say, maybe the internal moment at that location, but it's increasing the overall destabilizing effect, and so that's okay. You don't have to start chasing plus and minus, and when does it increase, when does it decrease the moments or other forces at a given location. It's only the overall destabilizing effects. When we look at stability critical structures, remember we're not required to put on the out-of-plumbness or the notional load unless the structure is stability critical. Then we would apply the delta naught over L or the N sub I in the direction of the resultant of all the lateral loads. Pretty much as simple as that. Generally, it's considered that we don't need to consider a torsional notional load or other corresponding initial twist of the structure. Basically, the ASC 7 or other eccentric wind, accidental seismic eccentricity loadings are sufficient generally to address any torsional concerns. Last thing in terms of looking at notional loads, if we have a gravity-only load combination, if you just look at it from the mechanics, if it's only gravity load, you can't have any total net foundation shear. But often engineers are puzzled by the fact that, hey, I put all these notional loads on here, and now I've got a sum of all my notional loads acting on the foundation. What's missing there is basically the way we derived the notional loading, and we did not carry forward into the specification the fact that we've got a P delta shear that is on the foundation that really we should be bringing forward and putting at the foundation. If you put that P delta shear force at your foundation level, you'll generally get non-zero individual shear forces in a given frame, but the overall result that you'll have with those P delta shears applied at the foundation level will be the correct being zero total lateral load associated with a gravity-only load combination. All right, so let's get down to doing an example to kind of see if we can make sense out of these different things. The example I'd like to show you is just a single-story frame here. Again, we'll look at a multi-story frame next week, or building next week, and we'll look at some other examples in the week after that. This particular frame has lateral load resisting columns just at the end columns, the outside columns on the frame. It has a roof girder that spans continuously over all the interior columns, which are relatively light columns. We're assuming that we're not making moment connections of those columns into the rafter or into the roof girder. All the column bases are assumed to be simply supported, and so all these interior columns are leaning columns here in this structure. The member sizes, the different span lengths and story heights are shown here. Also, we're looking at two LRFD load combinations and the things that are presented subsequently involving dead load, snow load, and wind load. The columns are braced out of plane, top and bottom. The girders, let's assume they're braced at 5 foot on center by purlins with flange diagonals to the inside or bottom flange of the roof girder where required. We're going to use these particular properties for the W12 by 65 lateral load resisting column and the W24 by 62 roof girder as we go along. Also the PY value of the column and the PMN values of the column and the roof girder are shown here. These are basically taken out of the LRFD or the AISC manual, and so we'll just work from these and use them in our strength checks as we're moving forward. Now the big picture with this particular frame, many of my students often think that a tall structure is where we get large second-order effects. It's actually not the case. It's structures like this that are relatively squat, and so there's relatively small lateral load requirements, say from wind, but we could have a wide footprint, so we have relatively large total gravity load. Also, if we have a single-story structure, and if a lot of times these structures don't require that we restrict either seismic drift limits or wind drift limits to small values to avoid damage to cladding or interior partitions, etc. Many times the non-structural or structural items on the structure are able to take a relatively large drift. And so these structures can be fairly flexible, but with that wide footprint up there, we've got a lot of gravity load on a small lateral stiffness, meaning big second-order side sway effects. Now, I'd like, in what we move forward with showing here, I'm going to show some results, basically how we could do the calculations and pull it together, the first-order amplified analysis, but also then compare to what we'd get for this structure with a general-purpose analysis. Kind of the amplified first-order analysis is kind of more tedious and more of a pain in the neck here, a lot of different details. Kind of to simplify some of those, I'd like us to look at doing just a base analysis with unit lateral load. And so the internal moments and axial forces due to that unit lateral load are shown here. We're going to have different lateral loads in the things that we move forward with. And so what we're going to do is basically take these results for unit lateral load and scale them up by the actual lateral loads to get first-order analysis results for different lateral loading in the subsequent slides. Now, one of the things we could do with that unit lateral load is assess the story side sway stiffness. So working from last week, if we do that analysis, say in mass stand, we get a drift here under unit load of 0.2968. And so with the calculations that we'll look at, I'm doing this with a reduced stiffness of 0.8 E. Structures like this, usually the tau is going to be 1. The axial load's not going to be nearly high enough to kick the tau factor in to less than 1. And so we're just assuming that that's going to be the case here as we move forward. Now the first order story side sway stiffness that we looked at last week, PL story, is this total H divided by the drift ratio, delta H over L. And so PL story here is 808.6 kips per radian. It's somewhat informative to look at what we're getting from each of the columns. Essentially half of that story stiffness is coming from each column, so we'll call each column value a piece of L. And we could do a piece of L as generally a stiffness coefficient we'll call B sub L or beta sub L times a 0.8 EI divided by L squared. We take our value, basically 404.3, and then back solve for beta L. We get 1.884 here. If you remember the cantilever column case we did last week, beta L would be 3.0 for that. Or here in this case, if I have a pin base and if the roof girder were essentially rigid compared to the columns, we'd get beta L equals 3.0. So the beta L kind of gives us an idea of how much reduction we're getting due to the ideal case of rigid end restraint at the tops of the columns. We're reducing from 3.0 to 1.884. Now, again, to simplify some of the subsequent presentation, we don't have to do it this way, but we'll do a unit vertical distributed load on the roof girders, and here's the internal moments and axial forces from that will scale based on whatever the subsequent vertical distributed loads are from our ASC LRFD load combinations. Okay, let's get on to business. Let's look at load combination 1 in detail, so 1.2 dead plus 1.6 live. We need to consider the design by the direct analysis method. We need elastic stiffness reduction. We need nominal out-of-Plumbness. Let's look at doing this by what we talked about last week as the amplified story drift method to get our internal forces, MU and PU, say for design of the column. We'll compare the results from that to the ISC B1, B2 or NTLT method, and we'll also compare to general purpose analysis results. So moving forward with this, basically kind of a basic load takedown. Our distributed load for this load combination 1, 1.2 dead plus 1.6 snow, is 3.12 kips per foot or 0.26 kips per inch. And so if we total up that load acting on 5 bays at 40 feet, we get a total story in our LRFD load combination of 624 kips, or from that. The leeward column axial force is approximately 208.8 times this QU, working from the unit load results I showed you earlier. That's 54.3 kips. We need the axial load taken by moment frame columns, which is approximately 2 times PU, 109. So why are we doing all this? We basically need to get the R sub M factor if we're going to get the story amplifier B2. So R sub M is 1 minus 0.15 PMF over P story. That's 0.974 here. Let's check our column axial load level. We kind of expected that tau wasn't going to kick in. We're well below the limit of 0.5 PY, where we would have to consider a tau factor. So tau B is equal to 1. Let's get our story buckling load. And so the story buckling load, PE story, is R sub M times PL story, 787.6 kips. And again, you can see over to the right here, I'm showing you the equations from Appendix 8 corresponding to our calculations. Now the B2 factor is 1 over 1 minus P story over PE story. So we crank that out. We've got a B2, a whopping 4.814 amplification, which should kind of raise some red flags, but let's continue. And I'm kind of giving you a kind of an upper end extreme case here with this building, but you could legitimately say, given the ASC 7 rules and the relaxation of seismic drift requirements, if the walls, partitions, etc., can take it, a fairly liberal wind drift requirement, this frame could be designed. All right, notional lateral load. We need that if we're going to account for the out-of-Plumbness effect. And so we're going to go that direction here. So for a P story of 624, a single story frame, P story is Y sub I in our single story. So that gives me a notional load of 1.248 kips. What's the first order lateral deflection due to the notional lateral load? Now I'm looking at this on the frame, including effect of reduced stiffness. Unit load deflection was 0.2968, and so that means due to my notional load, the first order deflection would be 0.3703. So this is basically saying by first order effects, if the frame were leaned initially by 0.002 L, or 1 in 500 of L, Then you apply the loads from a first order. The gravity load from a first order effect would cause an additional 0.303 inches of deflection. But that deflection gets amplified by the side sway amplification factor. So the actual second order amplification in this frame is 1.782 on the drift, the amplified drift. Now by the amplified story drift method, we basically need the P delta shears, HP delta, that correspond to this, that we're going to apply along with the first order effect of that out-of-plumbness, the notional load N sub I. Now that HP delta is P story times the second order delta over the story height L. That's 4.633 kips. That goes on with the N sub I. The unit load effect in terms of axial force was 0.317. So that we add that. Essentially, this is an overturning effect on the leeward column, increasing our axial load on the leeward column from 54.3 to 56.2. Now let's look at our column non-sway amplifier. So here's the PE1 equation from what we talked about last week. We're just going to use K equals 1 in calculating this just to be conservative. We got 2118. We've got 0 moment at the base, maximum moment at the top. So C sub m from the equations we were looking at last week on B1 is 0.6. The B1 factor ends up being a number less than 1, and so we take B1 equal to 1, and that's almost always the case with a sway frame like this. So now we're ready to apply the amplified story drift method, and so we've got the effect, the gravity load effect, 0.26 is our load in kips per inch on the roof girders, times 7241 for unit load, plus 120 times the sum of Ni plus HP delta. Then we hit all of that by B1. If B1 is greater than 1, that's a conservative accounting for P small delta effects on the overall member moment. So we get an MU of 2588. If we compare to what we've got from the AISC NT-LT method, so everything is summarized here for this, B1 and B2 are the same, and we get the MU B1 MNT plus B2 MLT in this case, 2602. So very similar numbers. PU, essentially the same numbers I just showed you, 56.2 on the leeward column. If we look at what we've got with the comparison to a general purpose second order analysis, the general purpose analysis, if we measure delta second over delta first at the mid-width of the frame, is 4.515, so not quite as high as what we estimated. That's conservatism is actually coming in from the R sub m. The R sub m effect is not as high as what we actually estimated in this frame. And then also same type of thing on PU and MU. The general purpose analysis gives a slightly smaller moment and smaller axial force in this leeward column. So you could say that we could have skipped everything with all the first order amplified analysis and just done the general purpose analysis. But you can also say that doing the amplified first order calculation kind of helps us to get an appreciation of what's going on here. All right, so we need to do some strength checks. The columns are braced only top and bottom out of plane, and so we need to look at the L over Ry in assessing their strength. FEY here, pi squared E divided by L over Ry squared at 45.3 KSI. Notice there's no stiffness reduction here in this equation. Let's look at the applied axial load stress, our 56.2 over the gross area, and so that's 0.064 in terms of FU over FEY. That's less than 0.1, and so if we use the extension from Design Guide 25, we basically have a situation here where the axial load is very small, and so that extension is basically saying, hey, for this kind of a case, you basically have very little error associated with just using phi py as your column strength. It's phi py here because the column has a non-slender web. So the form factor Q is equal to 1 for these columns. In terms of getting the flexural resistance, the length of our columns is 20 feet. The columns basically had 0 moment at the bottom, maximum moment at the top. And so I'm going to use an equation from the commentary that gives me a little bit higher lower bound C sub B, 1.75. We have the phi MP prime for these columns. They have a non-compact flange, and so 356 foot kips, so 4272. The L sub R on this column, 435.1. If we basically recognize that we are basically at an embrace length less than L sub R, which is putting us pretty close to already being at the plateau strength of phi MP prime, the C sub B of 1.75 is definitely going to put us up on the plateau. And so by inspection, we can basically say, okay, if phi MN is phi MP prime, essentially the flange local buckling, phi MN 4272 here. So now let's do our beam column check. Pu over phi PN, 0.065, less than 0.02. We combine everything in here with our moment and our moment capacity, and so our unity check is 0.63. So we're well less than 1. Does that mean that now we can apply 56% more load to the structure? No, that's never been the case. In the effective length method, though, the unity checks tend to scale close to linearly for a lot of structures. But definitely when you're using direct analysis method with a frame like the one we're looking at here, you have to be very careful not to make that mistake of assuming that you can basically, I've got a unity check of 0.64. I've got a little extra load that got added to the structure. Yeah, no problem. You got to check it. You got to be very careful for gravity-only load combinations because it can be very sensitive. And it is a stability critical frame here. There's also roof girder checks that are shown in the slides, but a fair amount of detail there. It's really just a matter of using fundamental equilibrium given the girder end forces and applied loads on the girders, and then comparing to flexural resistance checks from Chapter F of the specification. All right, so Brent, maybe this is a good place to take a few questions if there are any again, and then we'll look to kind of wrap this up in terms of some comparisons to simulation and synthesis of the concepts.
Okay, let's just take a couple questions here, and then we'll wait for the rest of the end.
Okay.
These, let's see here. This is a question in regards to an existing structure. If you are assessing the conditions of an existing structure, which method is appropriate? Is there any restriction to using the direct analysis method?
Okay. Maybe take an example here. Maybe you've got a structure and you actually you've taken some measurements. Someone that basically showed you that, hey, this structure is out of plumb by more than the code of standard practice. The specification basically says, okay, hey, you don't have to use 0.002. In fact, on a structure like that, you would use what you've got. And so direct analysis would give you a more general way of checking. Say if you have a situation where the structure does not meet the code of standard practice.
Okay, and kind of a question regarding the ability to use the direct analysis. The question is this, I'm sorry, I'm struggling here. Here we go.
Right.
This is the next question in regards to the use of the direct analysis method. Would a pure cantilever column loaded at the top qualify for K equals 1?
Yes, because if you're using the direct analysis method, you're incorporating a stiffness reduction and a geometric imperfection effect in your structural analysis. And so the side sway stability effects are basically captured within the analysis. You bring those required forces from that analysis in to then check the member or check the connection.
Okay. Then one more question here before we hit on this last section. How are small delta effects typically modeled?
Okay. Let's hold that one for next week, or actually probably the week after next. I'm going to provide a fair amount of discussion on that question 2 weeks from now.
Okay, sounds good. Let's go ahead and finish up, and we'll have some more questions at the end.
All right, super. Okay, so let's kind of look at how things work if we were to do comparisons of our DM, and also we could do the ELM. I didn't show you the ELM, but the ELM solutions to test simulation results. And then we'll kind of use that to kind of try to wrap up. And so what you see here is a plot. Vertical axis is the fraction of the design load for load combination 1. There's also slides that I've included for load combination 2, but we're going to focus on load combination 1 here. The horizontal axis is the story drift, delta over L. And so traditionally in effective length method, this is a symmetric frame, and it would be loaded symmetrically for this gravity-only load combination. And so there wouldn't be any side sway traditionally. And so we basically just go up the vertical red dotted line until basically our column checks. Now we would have some moment in the lateral load resisting column that's coming from the gravity load, but basically as far as plotting story drift versus fraction of design load, we're not seeing any drift. Now the bolder red curve is basically what we get effective length method by including the out-of-plumbness in the analysis. Then it's more true to what the actual structure is doing. And the actual structure is basically represented here by a distributed plasticity analysis, which is conducted based on the requirements of Appendix 1. And Ron's going to talk about that some, I believe, the last week of the course. But you can basically assume that this is an actual test simulation, but it's a test simulation with a nominally reduced stiffness per Appendix 1. Now, the dark blue curve is what we get from the direct analysis method. You can see it's tending to undercut things a little bit here. So the direct analysis method isn't perfect, but generally it gives a better characterization of what the actual test simulation is doing. I'm showing you a blue dashed curve here that kind of shows what we would get if we used a reduction of 0.9 on the elastic stiffness, which is actually the reduction Appendix 1 says to use if you're doing a good job of modeling all the distributed yielding in the structure. We're not quite doing that with the analysis we're using here for our direct analysis method. The point, the basic stiffness reduction is kind of coarse, but actually the 0.9 would be closer to the truth for this particular frame. Okay, so kind of the mantra here in looking at these is that we're doing a little bit better job with capturing what we would get from a test simulation if we use direct analysis method. You can see labeled on here that what happens is we actually form a plastic hinge in the girder, and that would be our first strength limit for elastic design. If we continue this with what Ron is going to be talking about some in the last week of the course, we basically insert a plastic hinge at that location and we keep pushing. We get a little more capacity out of this frame before a second hinge forms, and then that's it for the structure. We reach a collapse load. And this is basically the way this structure would look in mass stand. Again, the hinge shown over the first interior column on the left is basically where we would stop in elastic design. The hinge at the top of the leeward column is when the frame finally gives up the ghost here. Now, this plot is maybe a little more directly informative in terms of comparing the effective length method and the direct analysis method. What you see here are two strength envelopes. The red dashed strength envelope is what we get from the effective length method. And so any of the strength envelopes here are always based on anchor points on each of the axes. So the horizontal axis is the moment axis, and so the anchor point for the envelope there is VMP prime for our frame, 356 foot kips. It's the same direct analysis method or effective length method. However, the anchor point for the vertical axis is very different in these two solutions. With the effective length method envelope, we calculate an effective length factor which is on the order of 5.0 for this frame, and that's so big because we've got very large leaning column effects from all the interior leaning columns in this structure. And so that big effective length factor on our columns knocks down our VPN based on KL to 69.2. That's our vertical axis anchor point for effective length method. Believe it or not, the vertical axis for this leeward column in the direct analysis method here, if we use the Design Guide 25 rules, is VPY, 860 kips. So basically more than 10 times VPN based on KL. All right, how does all this work? Well, the light red curve is what we get from a force point trace, basically tracking at the top of the leeward column axial force versus moment as we load up the structure. Traditionally, with a zero notional lateral load, essentially looks linear. When that load basically intersects, or that force point trace intersects the strength envelope, that we're done. That's it. We say, okay, we can't go any further now from in an elastic design. The dark red curve is what we get, changes things a little bit by including the notional lateral load corresponding to the out-of-plumbness. But if we look at what we're getting in the test simulation, it's the green curve, and it keeps trucking along until we basically get to close to a cross-section strength at the top of this column. Actually, we formed the first plastic hinge in the girder at the dark blue dots there along the force point trace curves. But if we put a plastic hinge in there, Appendix 1 basically allows us to use direct analysis method and keep on moving along until we basically have reached a mechanism in this frame. And so much closer tracking of what we're seeing all the way through to the real capacity of this frame with the direct analysis method. We're basically getting, if we go that route, 46% more strength for quantifying that strength in terms of the axial load we're able to develop in the leeward column at the strength limit. But what goes along with that? Well, basically, if we're going to go there, our girder is going to need to take 133% greater moment. And so we need to pay a price for the moments in the girders with this. All right, that kind of gives you a flavor from the specific example here, but let's kind of wrap up by looking at things kind of more generically, comparing effective length method and direct analysis method. Both of these procedures are using the same base beam column strength interaction curve or unity check that I'm labeling here and giving you the equations for again. But if we look at the effective length method, the anchor point essentially on the vertical axis here for the column strength is calculated based on KL, where K generally for most of the columns in a sway frame is going to be greater than 1. Correspondingly, with the routine application of the direct analysis method, we generally would calculate the column capacity based on the actual unbrace length L. And so, therefore, the anchor point is much higher generally on our vertical axis for the strength envelope, the dash curve here in the direct analysis method. Now, with the direct analysis method, if we're looking at the force point trace, how's P&M varying as we load up the structure with our load combination? The direct analysis method, it's not perfect. It's what Ron referred to in one of his earlier talks as a poor man's test simulation analysis. But generally, you're going to get internal forces that track more closely to what you would actually see if you were to test the structure with with nominal stiffness, with stiffness reductions based on Appendix 1, and with strengths essentially based on a factored Fy. Ron's going to talk about this more during week 8. Effective length method kind of tends to drift away from the actual response in the internal force point trace, but we basically cover the bases with that by the PR or the PN calculation, PCKL versus PCL here. And so when both methods are working well, if we take the capacity of this structure essentially as the axial force we're developing in this column that we're checking, both methods essentially end up showing roughly the same axial force capacity. Now, the internal moments, the direct analysis method generally is going to show, particularly if we have something that's a very severe stability critical frame, which I essentially gave you a quite extreme example of here. The internal moments generally can be, in that type of structure, quite a bit larger. And that's why we start to worry when we're using the effective length method and the spec disallows the method. Once we're getting to these sorts of frames, we can have situations where we're not really tracking very well the true internal force in our connections, in our beams, etc. And so we want to go to the direct analysis method to make sure that we're getting appropriate internal force levels. So in summary, both of these methods are legitimate. You could say that the direct analysis is a more accurate representation of what the structure is really doing, as long as your second order analysis calculations are accurate. And so we need to always be mindful of the requirements we talked about last week to ensure good accuracy of the solution. The effective length method requires some additional restrictions to guard against its more limited ability to represent the actual internal forces. And so that basically means the inclusion of a minimum out-of-plumbness effect for gravity-only load combinations. The traditional effective length method in prior specifications did not require any out-of-plumbness effect or notional lateral load effect, but the current specification requires, with effective length method, we do that for gravity-only cases. And in addition, basically once we get to a structure where if we're checking things based on nominal elastic stiffness, which we would use with the effective length method analysis requirements, if the side sway drift amplification, delta second over delta first, is greater than 1.5, we basically say, oops, we're either going to have to stiffen up the structure here to do the calculations with effective length method, or we need to switch over for that particular case and look at making the assessment with the direct analysis method. Okay, that's it. I hope that was useful. And Brent, I guess we have a few more minutes where we could take some questions again if there are any.
Okay, thank you very much, Don. Let's try to address a couple more questions before we wrap up for the night. Question is on slide 36. If you could go there, please. Okay, the question is it acceptable to use a K equal to less than 1 for a brace frame if the connection warrants it, in conjunction with the direct analysis method?
Okay, very, very good question. If it's a braced frame, the direct analysis actually gives you probably a more representative result in terms of the overall stability effects. It is acceptable to use K less than 1 in that case. I had mentioned that we could use K less than 1 with the direct analysis method earlier. And in addition, with the caveats I provided, you could use K equals 0 for that matter and just work from the cross-section strength. Yeah, that's appropriate. Now, actually, this is one thing I'm going to point out next week. If you have a braced frame, you don't really gain any advantage typically by going to the direct analysis method. In that case, you actually gain an advantage. The internal forces will not be quite as large if you do have some second-order effects because you're using the nominal stiffness. And so many engineers would just prefer to use effective length method and go with the traditional approach if it's a braced frame structure.
Okay. Next question: if your delta sub 2 over delta sub 1 is greater than 1.7, does this mean that the only way to design it then is to use Appendix 1?
No, it means that direct analysis method is required. You could also use Appendix 1. Basically what the specification says is that that type of structure, you would not be allowed to use the effective length method, or you would need to stiffen the structure so that you bring your side sway amplification below that limit to use the effective length method.
Okay. Next question: can out-of-straightness be modeled with notional loads? Oh,
another good question. Yes, it can. I think the comment I made earlier would be the way I tend to lean on it, and that's that it's much more straightforward conceptually, and you could say in terms of implementation, just to put the actual imperfection in the model. But very similar to the way we derive the notional lateral load for side sway, you essentially could use the same process with whatever out of straightness you're trying to model, and you say, okay, let me segment my member, and then basically look at each segment and get my P delta shears, and from that you can get the corresponding notional lateral loads for an out of straightness.
Okay, and one last question. The question is, what is, let me try if I can rephrase this. When is the notional load case going to control or be significant if the notional loads are typically less than lateral loads due to wind or seismic? Okay.
Yeah, so the deal there is what I had mentioned early on about stability critical versus stability non-critical frame. And so if you have a frame where by the AISC specifications it's the delta 2 over delta 1 is less than 1.7 in the direct analysis method, we're basically saying, yeah, you would see some effect of running that lateral load combination with a notional load effect or versus without, but that effect is starting to tend to be rather small. And so then as a design engineer, we're basically saying, you know, why did I do all this? It made very little difference. On the other hand, if it's a stability critical structure, similar to the extreme example I provided here tonight, if you basically look at the notional load or the strength calculations there with and without the N sub I on there when we did the second order analysis calculations for our one-story frame tonight, you'll see that it has a measurable difference in terms of the internal forces and the values that we reach in the unity check. So basically, the code or the specification is giving you an out to allow you to use simplifications and not bother with things that are rather small for stability non-critical frames. But if you have a stability critical frame, the direct analysis method rules basically say you shall include your out-of-plumbness or your notional lateral load with your lateral loads in those cases.
Okay. Well, thank you very much, Don. And we've got a few more questions. I'll follow up with you after the conclusion. But that does it for tonight's session. Next week we'll be here same time, same place. However, be aware that next week we will be at daylight savings time. So for those of you that are in a time zone that does not participate in that, will be 1 hour earlier. So again, next week is daylight savings time. Thanks again to Dr. Don White, and thank you all for joining us. And we will see you next week.